folks, and welcome to this Introduction to Calorimetry. By the end of this lesson, you should be able to understand how the technique of calorimetry works and explain the assumptions that are used in calorimetry questions. So first off, calorimetry is the method that you use to find that thermochemical data for your reactions. So you probably, if you have been looking in your textbook, your data booklet, or anything else, the information about the heats of reactions, there are loads and loads of lists out there where you can reference the information for these reactions. And generally the way that you would find them is through calorimetry. The way that you use calorimetry is you set up a system and it will have its surroundings. You are going to have the enthalpy changes in the system affect the surroundings, and it's the surroundings that you measure these changes in. You find out where heat is coming and going and that sort of thing, and you use that data to then make assumptions about your reactions. So the technique itself is referred to as calorimetry, and the tool that you would use is referred to as a calorimeter. There are many different tools that you can use for calorimetry. Some of the big ones that you will probably see a lot are coffee cup calorimetry, and there's also something called bomb calorimetry, where the bomb is a very well insulated container that has a little place for the reaction to happen, and then it's also surrounded by water inside this larger container. Now, some of the reasons why we can do calorimetry in the first place is because of a property that is called heat capacity, or the specific heat capacity. Heat capacity itself is the energy required to raise the temperature of a thing by 1 degree Celsius. If you have any particular object, then it's going to be set that when you need to raise the temperature of the thing by 1 degree Celsius, it's always going to be consistent in terms of how much energy you need. Now, heat capacity itself is not going to be very useful to us because heat capacity is for a very specific object made out of very specific things and of a very specific mass. So you would have the heat capacity of this specific coffee cup, or this specific bowl, or this specific beaker. If someone else is using a different beaker or a different bowl, then the heat capacity of what they're using is going to be different. So instead, what's more useful is to use the specific heat capacity. So this is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And these are also properties of materials, and so you will be able to find them in various databases. When it comes to specific heat capacities that you're going to use, or things that you're going to use as surroundings for the different reactions that you would do, it's typically going to end up being water. The reasons for this is because it has a pretty specific heat capacity, so it takes up a lot of energy to make it rise by 1 degree Celsius. It's also a really good solvent, and so it's a very good surrounding for many different types of reactions. It's also, on top of all of that stuff, really easy to get and to use. And so for most questions that you're going to do, you're going to be using the specific heat capacity of water because that's what your surroundings are probably going to be. Now, in this day and age, the standard sort of unit that you're going to use for energy is going to be joules or kilojoules. But in the olden days, what they actually used to use, the unit that was used much more in terms of energy, was calorie. And you've probably heard about this unit before, mostly in the context of food, because it's still actually used in that context. Calorie is actually the energy required to raise a temperature of 1 gram of water, specifically, by 1 degree Celsius. So 1 calorie is the energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, this isn't something that you need to know for this course. I'm not going to be having you try to calculate things in calories, but as reference when it comes to looking at things in the real world, You are going to see calorie, but there's also the unit of calorie, which is spelled with a capital C, and the two are actually different. This calorie with a capital C is actually the same thing as kilocalorie. So 1,000 small c calories is the same as 1 kilocalorie, or one big letter C calorie. But as I was alluding to earlier, we're going to be using water for the most part. Is going to be 4.184 joules per gram per degree Celsius. So for 1 gram of water, to raise it up by 1 degree Celsius, it's going to be 4.184 joules. Now you may encounter molar heat capacity as well. It's unlikely, but it's possible, in which case it's the same idea, energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. That's all it is. So here's how calorimetry problems work. As an example, we're going to take some solid sodium hydroxide and we're going to dissolve it in water. When you do this, your sodium hydroxide is going to dissociate and form the ions in solution. And this particular process, where you're going from that solid to the ions in solution, it will release energy. So that whole process of making a solution is exothermic. Now from here, because it's exothermic, the surroundings, or the water that everything is dissolving in, are going to get hotter. So whatever heat, whatever Q, is lost by the system is going to be gained by the water. So while the heat of the system is going to go down, the heat of the water is going to go up. Now the thing is that quantity-wise, these numbers are going to be the same. But you can see that the signs themselves are the opposite of each other. When one is losing, the other one is gaining. This does not a good equation make, because the signs are the opposite way. But what we can do to make this into an equation is we can say that the delta H of the system, the energy change in the system, is equal to the negative of the heat changes in the water. So remember, you know magnitude-wise, if one of the things are going down, the other one is going up. So if it's exothermic and your system is losing heat, then your water is going to gain heat. Now, to make these things equal, you need to flip the sign of one of those sides. And that's what's happening by adding in that negative sign. Now from here, we know the heat change of the water based on the mass of the water, the specific heat capacity of the water, and the change in temperature of the water. And so, in most cases, the delta H of your system is going to be the negative m times c times delta T of your water or surroundings. Now, if you have several different things that are making up your surroundings, so say, for example, instead of just water, you have water and a metal cup, which is also going to change temperature, then you just keep on adding them all to this side of the equation. Now, this being said, you still need to set up your calorimeter properly so that your data is still going to be valid. And for this, you need a specific kind of system. When it comes to these systems and surroundings, there are you can categorize them into 3 of them. The first one is an open system where particles and energy can enter and leave freely. Now, this one is going to be problematic for your calorimetry because remember, in calorimetry, everything is stoichiometric. So if things keep on coming in or keep on going out, that means your reaction isn't going to complete exactly with the quantities that you originally were starting with. So you don't know exactly how much energy is being produced or absorbed because your particles, you don't actually know which particles have actually reacted. Now, the second type of system is a closed system. And in this particular case, particles are always going to stay in their specific system, but energy can enter and leave freely. This is the type of system that you want when you're doing calorimetry, because You make sure the particles are always staying inside your system. But the thing is that if you think about your sodium hydroxide and dissolving it, that situation, you have no way to measure the heat changes with solid sodium and sodium ions as they are. We need that medium of water to be able to actually measure what the temperature change is. And so, yes, you're going to keep your reaction contained within your beaker of water or whatever calorimeter you're using and water, and the heat from that dissolution is going to go into the water, for which you can actually measure that temperature change very easily. Now it seems that the isolated system might be the best for calorimetry, but again, you can't use an isolated system because we have no good way to measure what temperature changes happen with a lot of the reactions that you're dealing with. So, no isolated systems for us. So here is an example of a calorimetry question. Pause the video, take a read of it. Alright, so it's going to ask for molar enthalpy, and you can see that all of this is happening inside of water. So our system is your KCl dissolving into the ions, and then your surroundings are going to be the water. So if we set up our equation, it's going to look like this. So we know that we have to find out what the enthalpy of the system is going to be. It's going to be the same magnitude but opposite sign or opposite direction of your of the water, the surroundings. And so when we set everything up, we have the mass of our water, we're going to multiply it by the specific heat capacity of water, and then for a temperature change, we're going to take the final temperature and subtract it by the initial temperature. Now, this is one of the very, very few situations in chemistry in general where you're not going to change the temperature into kelvins. The reason for this is because if you do all the unit conversions, the change in temperature, whether it's in degrees or kelvins, is going to end up the same anyways. So if we're being technical, you could change it to kelvins and then do the change in temperature, but you're just adding in extra steps that's going to get you to the same place. A degree Celsius is the same as a degree change in kelvins. Now if you take a look at what's going on here, you're going to notice, oh, the final temperature is actually lower than the initial temperature. So actually this is going to give you a negative number, which will make this entire thing positive, and so actually this whole reaction is endothermic. Another thing you might notice if you're a very detail-oriented person is there are a lot of shenanigans going on here. Because first, it said 100 mils of water, and yet we're using 100 grams. What's happening with the KCl and the mass of that? And, well, if you mix water and KCl together, you're not going to have water anymore. Does the specific heat capacity not change if that's the case? So, when you are solving these problems, there are going to be a bunch of assumptions that you are going to use for pretty much all the cases. So here are those assumptions. The first one is all the heat that was being absorbed by the reaction came completely from the water. Nothing else changed. Your container that you were doing this was a perfect insulator and it didn't change temperature, so none of the energy was taken from the container. Nothing had leaked outside or nothing from outside of any of this leaked in. The second one is that the specific heat capacity and density of the surroundings, so that water, it stayed the same as water. So yes, technically, the density and specific heat capacity would change a bit because now you have a solution instead of actual water, but the change is going to be so small in difference that once you get significant digits and everything involved, it's not really going to change your answer anyways. So the assumption is usually made that those things don't change. And the last bit is that what you're measuring in terms of the temperature change of the water does accurately represent the change in heat. In the next lesson, we will be diving a little bit deeper into the solving of calorimetry questions, but in terms of this one, that's all for now, and I'll see you next time.